Hello everyone, welcome to the part 3 of the AMC 8 2026. Today I'll be covering problems 18 through 22. I'm going to go through at full speed, and once again, pause the video if you need, if I'm going too fast. Alright, problem 18. In how many ways can 60 be written as the sum of two or more consecutive odd positive integers that are arranged in increasing order? So this is going to be an arithmetic sequence with common difference 2. So immediately you can probably see 29 and 31 works. So these two are odd, they're consecutive, and they sum to 60. So this is one that works. But let's rigorously prove or find every sequence that works. So let's say in a sequence of odd integers, let's say 3, 5, 7, 9, the sum of these is actually the middle number right here. This is 6. Let's call the middle number m, times the number of numbers. Let's say it's n. So there's 4 numbers here, and we can pair these up. 3 plus 9 is 12. 5 plus 7 is also 12. So the sum of these is actually going to be m times n, which is 24. So we notice that n must be even because the sum of an odd number of odd integers is odd, and 60 is clearly even. So it must be, or n must be even. Let's just n equals even number. So this means that a sequence like 3, 5, 7 would not work because the number is odd. This also means that the middle number m must also be even, because the middle number here is between two odd numbers. So m is actually 6, which means m and n are actually both even. So we want m times n equals 60. And we can list them out. M and n can be 2 and 30, 6 and 10, 10 and 6, or 30 and 2. So let's just take this one. This actually corresponds to the thing earlier, 29 and 31. And this corresponds to, if average is 10, then we have 9 and 11 on the sides, and 7 and 5. So by this formula, we know that this must add up to 60. But if we try this one, the center is 6, so we have 5 and 7 on the outsides. But if we go this way more, 3, 1, we get to -1 and -3. But those are negative, so we can actually use these. And same thing goes for, so this one is not allowed. Same thing goes for this one, because this would be even more negative. So we actually only have these two sequences that work. So the answer is B2. Next, problem 19. Miguel is walking with his dog, Luna. When they reach the entrance to a park, Miguel throws a ball straight ahead and continues to walk at a steady pace. Luna sprints towards the ball, which stops by a tree. As soon as the dog reaches the ball, she brings it back to Miguel. Luna runs 5 times faster than Miguel walks. What fraction of a distance between the entrance and the tree does Miguel cover by the time Luna brings him to the ball? So we have the park entrance here. This is Luna's path, and this is Miguel's path. So we're given that L is 5 times bigger than M. And let's say this distance is D. So we know that L plus M equals 2D. If we substitute this in for L, we get 6M equals 2D, which means M equals D over 3. Which means Miguel's distance is 1/3 of the total. So the answer is D, 1/3. Problem 20. The land Catania uses gold coins and silver coins. Gold coins are 1 millimeter thick and silver coins are 3 millimeters thick. In how many ways can Taylor make a stack of coins that is 8 millimeters tall using any arrangements, assuming order matters? So let's think about how many of each coin we can use. So we can use 8 gold coins, 8 times 1, and 3 times 0 because there are 0 silver coins. We can replace 3 gold with a silver, 5 gold coins, and 1 silver coin. We can do that again. 2 gold and 2 silver, and we can't go any lower. So these are all. So we have, let's say, we have 8 gold here. There's only one arrangement for that, which is one on top of each other. If we have 5 gold and 1 silver, this is an S. We have 6 choose 1 ways. The S can be any of the 6 positions, which is 6. If we have 2 gold and 2 silver, there's 4 choose 2 ways. So adding these up together, we get 13. So the answer is D. Problem 21. Charlotte the spider is walking along a web that is shaped like a 5-point star. The web has 5 outer points and 5 inner points. Every time Charlotte reaches a point, she randomly chooses a neighboring point and moves to that point. Charlotte starts at one of the outer points and makes 3 moves. Revisiting points is allowed. What's the probability she is now on one of the outer points? So I'm just going to draw this. So I have 5 inner and 5 outer. She starts at one of the outer points. Without loss of generality, let's just say it's this one. So at position 0, which is, let's say time equals 0, there's a 100% chance that she's at the outer points. Let's just label this. P is a probability. So we want the probability at t equals 3 after 3 moves. So after 1 move, there's actually a 0% chance that Charlotte is at the outside because there's only 2 paths and they all lead to the inside. And then after that, from time 1 to 2, there's 2 paths back to the inside and 2 paths back to the outside. So this is again 1/2. For 3, if Charlotte is at the outside with probability 1/2, then on the next turn she must be on the inside. So that's probability 0, and there's a 1/2 probability that she's on the inside, and multiply that by another 1/2 that she randomly walks to the outside. So this is a 1/4 chance of being on the outside. So the answer is B, 1/4. Problem 22. The integers from 1 to 25 are arbitrarily separated into 5 groups of 5 numbers each. The median of each group is identified. Let m equal the median of the 5 medians. What's the least possible value of m? So we separate into 5 groups. Let's just say the medians of these 1, 2, 3, 4, 5 are in order. So for example, we could have 1, 2, 3 as the smallest one, as the 3 smallest ones in this category, in this group, and then 4, 5, 6, and then 7, 8, 9. And then we could continue this 10, 11, 12, 13, 14, 15. So after this, we'll have to add 2 extra numbers into each group to finish this set. But in the medians, for the medians, this is the median, this is the median, and so the third smallest number is the median of each group. And the median of these medians, the middle one, is 9. So big M equals 9. And 9 is actually the smallest possible answer we see. They give answers 9, 10, 12, 13, 14. So we're actually done because there's no better choice and we found an optimal choice. But let's just prove that this is the smallest. So this number, let's just call, instead of 9, let's call M, because we don't know what it is. This M must be smaller than all of these, or it must be bigger than all of these, must be bigger than all of these, because the median M is bigger than the median 6, and also bigger than the median 3. And also must be bigger than these two, because it's a median of its own set. So this proves that M must be at least 9, because it's for sure bigger than 1, 2, 3, 4, 5, 6, 7, 8 numbers. And the 9th smallest integer is obviously 9. So the answer is A, 9. Thank you guys for watching. I'll see you in the next one.